Buenas noches, good evening, everybody. Welcome to day one on week 11 of the semester. So today we are going to finish chapter 6 material, and then we're going to move on to chapter 7. So last time we were talking about the concept of polysaccharides. When it comes to polysaccharides, understand that they are going to be biomolecules that are made of a single unit of monosaccharide, and the ones that we are going to be focusing on, at least in the chapter, are all going to be polysaccharides of glucose. As you can see specifically right here, glucose is going to be the subunit, in other words, the monosaccharide that every single one of these polysaccharides is built from, okay? So the alpha or beta in the glucose, remember that it is determined by the anomeric position, which is that position that forms when the carbonyl in your monosaccharide gets transformed by the OH that determines D and L configuration in the carbohydrate. Remember that that's where the alpha beta comes from. If you need a reminder of that, let me just go back. Is this concept. So the carbon that is right here, that's the one that is the anomeric position, and depending on where the OH is, that's what determines alpha or beta. Remember that I showed you guys that if you look at that position, if your sugar is beta, then the OH is going to be pointing up, while if you have alpha, as you can see here, the OH is pointing down. But again, every single one of these polysaccharides are built from specifically glucose. Now, what is the difference between these polysaccharides? Remember that cellulose specifically is going to be found in plant structures. So fiber is going to be one of those plant structures that is made out of cellulose. Starch is just the way that plants store sugars, okay? And starch has actually two different types of polysaccharides. One is called the amylose, which is a straight chain, as you can see right here in the bottom, that it makes a little bit like a helix. And then we have amylopectin. And amylopectin is going to have branches. So as you can see here, and I'm highlighting right now, it actually has branches extending from the main chain. Now, when it comes to glycogen, this is also known as animal starch. And the reason why it's considered animal starch is because this is how we store sugar. We may not be storing every single biomolecule. One of the two that we do store in the body that is utilized for energy, it is actually sugar in the form of glycogen, okay? So understand that that is an important way in which we store sugars. Now, in addition to that, the last thing that I want to mention when it comes to carbohydrates is that carbohydrates are very important in determining blood types, okay? So let's understand that the red blood cells in their outer layer actually have different combinations of sugars. And understand that blood types are based, as you can see, on 3 to 4 monosaccharides, okay, that are attached specifically in the outside of the red blood cell. Each blood type has the following monosaccharides: D-galactose, L fucose, and then N-acetyl D-glucosamine. That's just the names for them. Now, let me ask you guys really quick. By looking at the D-galactose, is that alpha or beta? The D-galactose, is that alpha or beta? Thank you, Kiyomi. Exactly. This is alpha. For those students that are like, wait, where do you see that it is alpha? Right here. You look at this carbon, my OH is pointing down. And remember that I told you guys this little acronym that I actually created when I was in graduate school. That is called BUDA, which means beta, up, down, alpha. So if that position on your Haworth projection, so the anomeric position, the OH is pointing down, that's alpha. If the OH is pointing up in the anomeric position, and the anomeric position in a Haworth projection is always that corner, then if the OH is pointing up, then understand that that is beta. Now, here, typically, to be honest with you guys, when it comes to carbohydrates, they are symbolized by different geometrical shapes. And you can see here that galactose is going to be a circle. In this case, they color it yellow. N-acetylglucosamine, they color it blue and they put it in a square. Then we have fucose. Fucose is that red triangle. And then we have N-acetylgalactosamine, which is just a brand new sugar that was not introduced here, just because that one is special and is only found, as you can see here, in the A blood type. But as you can see here, when we look around each one of the different blood types, and here we just have illustrated O, A, and B, where we also have AB, understand that what it was mentioned, that the 3 monosaccharides that we have here, they are illustrated. Let me just highlight them right here. So as you can see, every single blood type will have these, which is, as you can see, the galactose, the N-acetylglucosamine, and then the fucose. And as you can see, the difference between O and A is that they have the A antigen has an N-acetylgalactosamine, and then the B antigen compared to O, it actually has an extra galactose, okay? But this concludes all our talk about carbohydrates. Any questions when it comes to carbohydrates? Great. So now we are going to move on to talk about chapter 7. And in chapter 7, we are going to be looking at the attractions of molecules. So what we're going to focus first in section 7.1 is attractive forces, okay? Attractive forces, which are also known as intermolecular forces, are the forces that are found in between molecules. Now, understand that when it comes to these forces, the ones that are in between molecules, let me highlight them specifically. They are going to be categorized in between hydrogen bonding, dipole-dipole attractions, and dispersion forces. Now, There is one more that is discussed in the textbook. Okay, so other than the ones in the bottom, the other one that is included in the textbook is going to be an ionic, okay, attractive force. So technically, you guys need to know the ionic, the hydrogen bonding, the dipole-dipole, and the dispersion. So let's talk about them individually and let's understand how they each work. The first one is dispersion forces, okay? So what is a dispersion force? A dispersion force, understand that this is going to be present in any molecule that has electrons. So what does that mean in general? That all molecules are going to have dispersion forces. All of them, because they have electrons circling around. Now, this is how dispersion forces actually work. So we learned previously that when it comes to electrons and the presence of them in a particular molecule, the electrons are going to be circling around, circling around, circling around, circling around that positive nucleus. Now, let's understand that what happens in general is that since those electrons are going to be circling, and I'm just going to focus here, sometimes those electrons are going to position themselves in a molecule such that the electrons go and they are going to be in a part of the molecule, and then they're going to create what is called a temporary dipole. So it's not a full charge, it's kind of like a partial charge. That's why we have the symbol delta. Last time we talked about the delta symbol was when we were talking about a polar bond. So understand that this plus minus that we see here with the delta sign is because since the electrons are circling, 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 they're going to be positioning themselves in one corner of the molecule, and that's going to create what is called, again, a temporary dipole in a molecule. Now, if you have molecules, you know, just interacting with one another, and they're all the same, right? At times, the creation of one temporary dipole induces a temporary dipole in their neighbor. So as you can see here, these are going to be specifically two molecules that they have a temporary dipole. That's why you see here in parentheses a temporary dipole. And once the temporary dipole is created, they're going to interact with one another via the delta negative of one with the delta positive of the other, okay? But remember, the key for specifically dispersion forces is that you have a temporary dipole. So you may be wondering, what kind of molecules actually experience, okay, these type of forces? Well, here we have an example. So this is molecular fluorine. So this is what fluorine is specifically found in nature, which is a diatomic molecule, okay? Now, we already discussed this topic, but I want to bring it up again because it is crucial when we're talking about the different attractive forces. Fluorine is a linear molecule in which it has the same atom on either side. So it has symmetry. So let me ask you guys, when it comes to polarity, is this molecule polar or non-polar? Let's put it in the chat. Is this molecule polar or non-polar? Great job. Exactly. This molecule is non-polar. So if you have a non-polar molecule, the strongest attractive force that those molecules will have, just like you see in this example of F2, is going to be dispersion forces, okay? Now, understand that out of all the attractive forces that we have here in this particular table, dispersion forces are the weakest, okay? Now, let's move on to the other attractive force that we have here, which is called dipole attractions, okay? And in a dipole attraction, as you can see here, X and Y are going to be non-metals, okay? So if I know that X and Y are non-metals, what kind of compound is this? Ionic or covalent? Let's put it in the chat. If I have two non-metals, what kind of compound am I talking about? Great job, you guys. Exactly, a covalent compound. So understand that when it comes to a dipole attraction in a particular molecule, I'm going to have, number one, a covalent compound. But similar to dispersion forces, we're going to have those temporary dipoles. But what makes the difference in a dipole attraction is that I have a polar covalent compound. And if I have a polar covalent compound, understand that in my molecule, I must have a covalent bond that is polar. So these partial charges that we see here in between X and Y, they're going to be permanent dipoles, because I have a molecule that is polar. And remember that these dipoles are just representing the difference in electronegativity of two atoms. So in order for us to have a permanent dipole, remember that the difference in electronegativity needs to be higher than 0.4, but less than 2.0, okay? Now, to give you guys an example of a molecule that is going to have this specifically permanent dipole, we have here a simple molecule that is just made out of two halogens, okay? So this is bromine monochloride. So taking this into account, the bond between bromine and chlorine, the only thing that you don't see included here is going to be the lone pairs. But we know that here specifically, there's going to be 3 lone pairs on each. And let's understand that, as you can see here, bromine is going to be more electropositive compared to chlorine. So remember the trends in electronegativity. When specifically an atom is closer to fluorine, which is the most electronegative atom, that's where we get, so what I'm trying to say is, when it comes to the trends in electronegativity, remember that the halogens go fluorine, chlorine, and bromine. And as we go up in a group towards fluorine, electronegativity actually increases. So it makes sense that chlorine is going to be more electronegative compared to bromine. Now, taking that into consideration, understand that these dipoles are permanent. And since we have a polar molecule, then the attraction, or the dipole-dipole attraction, is between the delta negative of one molecule and the delta positive. But if we compare it to dispersion, understand that the difference is that in a dipole-dipole system, my molecule is polar. In the dispersion forces, my molecule overall is non-polar. and it's still covalent, okay? Let's now move on out of these to the next one, which is hydrogen bond, okay? So when it comes to hydrogen bond, there's certain parameters that we must meet. Number one, you need a polar covalent compound. And also you need the hydrogen atom bonded to a quote unquote fun element. Okay, so what is fun standing for? Fluorine, oxygen, or nitrogen. So if one or the other, both parameters need to be there. So if you have a molecule in which it's a polar covalent compound and you have a hydrogen bonded to fluorine, oxygen, or nitrogen, then the molecule can hydrogen bond. Because if you have a molecule that is covalent and is bonded to hydrogen, understand that that X, which is fluorine, oxygen, or nitrogen, is going to be more electronegative. So that's why you see here that X has that delta minus, okay? So the electronegativity difference between the two, remember that when it comes to hydrogen, hydrogen has on average a value of 2.1, and any of these, like for example, fluorine is, if I'm not mistaken, 4.0, oxygen is 3.5. So if any of these elements, fluorine, oxygen, or nitrogen, is bonded to hydrogen, then the molecules can interact via a hydrogen bond. To visualize an example of a molecule that undergoes hydrogen bonding, here we have HF. And HF, it has a polar covalent bond, which is that single bond that is connecting hydrogen and fluorine. And let's understand that specifically that bond, since what we are interacting with is another molecule, that hydrogen is bonded to one of those fun elements, that's where hydrogen bonding comes from. Again, if your hydrogen atom is not bonded to something in quote unquote fun, meaning fluorine, oxygen, or nitrogen, it cannot undergo hydrogen bonding. Now, the fourth type of force that I'm going to introduce to you guys is an ionic bond. Ionic bonds are the strongest attractive forces that is out there, okay? Now, it is important to note that different from the other forces that we have here, ionic bonds, the reason why it's the strongest attractive force is because we have full charges. What is the term that we use for when we have a positive ion? So what is sodium doing here? Great job, that's a cation. What about Cl minus? What is that called when we have a negative ion? Great, that's an anion. So see that this is different from the other symbols that we have down there. Because in the other ones, we needed the symbol delta to symbolize that it was partial charge. Here, we don't need the delta because these are full ions, cations and anions. And that electrostatic interaction between the cation and the anion is the strongest attractive force out of the four forces that we have seen, okay? So, in the slides, I actually integrated a flow chart that we can utilize in order to understand what are the attractive forces that are found in a particular molecule, okay? So taking this into consideration, let me just take a moment. And I want to give you guys a particular problem from the textbook so we can actually practice this. Let me get the image. Okay. Let me integrate it. I'm going to add the flow chart so you guys see how to utilize it to determine the attractive force. Okay. Let me share my screen. Great. So these problems that you guys see here are from page 301 in your textbook, okay? And even though we're going through 7.44, that's the one that I'm going to do with you guys, you can try on your own 7.43, okay? So we're going to utilize this flow chart to understand the different attractive forces, okay? The only ones that are included here that we will not be addressing, so let me just cross them right now, is going to be the ion dipole ones. Those are the only ones that we're not going to talk about yet. So taking that into consideration, okay? As you can see, in problem 7.44, it says, list all of the attractive forces found in each of these compounds, okay? So let's first look at CF4. So CF4, because it's a covalent compound, we always have to look at structure. If I draw the Lewis structure for it, this is how it looks like. Now, this molecule is a tetrahedral molecule that has 4 identical groups around the central atom. So we may have to revisit a concept that we haven't seen in a while, but it's very important for understanding attractive forces. So if we have a tetrahedral molecule, you guys, that have 4 identical groups around the central atom, is the molecule overall polar or non-polar? So tetrahedral molecule with 4 groups that are identical. I agree. This molecule overall is non-polar. So if a molecule is non-polar, what that means, you guys, is that the one and only attractive force that is going to be present here is going to be dispersion forces. And let me show you now how we utilize the flow chart. In the flow chart, it says interacting molecules or ions, okay? We can go, so this is step 1. Are ions involved? So for this one, the answer is no. Are molecules in are polar molecules involved? Our answer is no. As you can see, that takes us specifically to London forces. In other words, dispersion forces. London dispersion forces, London forces, or dispersion forces, all the same thing. Okay, let's move on to the next molecule. Okay, the only time that we have seen this molecule is when in chapter 4 I introduced to you guys specifically the functional groups. Okay, now let me specify that this is when we have to recall the information that we have done before. In this molecule, just if anybody remembers, what is this functional group? Does anybody remember? A carbonyl single bonded to oxygen. Thank you, Nikki. Exactly, that's an ester. Now, an ester has a carbon-oxygen bond. Okay, and if we look at the electronegativity difference between carbon and oxygen, let me look at my table. The value for oxygen is 3.5. The value for carbon is 2.5. This other oxygen is 3.5. Okay. So this molecule, what I highlighted in yellow, what type of bond is it? Is it non-polar covalent or is it polar covalent? Remember those rules that we learned previously. So at an electronegativity difference of 1.0, if that bond that I highlighted in yellow, both of them, the carbon-oxygen bond, is that polar or non-polar? Thank you, Vanessa. I agree with you. It's a polar covalent bond. So overall, this molecule is a polar molecule. Okay? So when you have a molecule that is polar and you're trying to list all of the attractive forces that it has, then because the molecule has electrons, it's going to have dispersion forces. Because the molecule is polar, it's going to have dipole attractions. Okay. Now, if we look at the flow chart that I was just utilizing, and let me just erase the work that we did for the first molecule. This is going to help you to determine the strongest attractive force. Okay. So interacting molecules are ions. As you can see, are ions involved? Our answer is no. Are these polar molecules involved? Yes. Are hydrogen atoms bonded to nitrogen, oxygen, or fluorine? What would be the answer to that? In an ester, do we have a hydrogen bonded to oxygen? Yes or no? Let me write in the carbons and hydrogen. This is a CH2, this is a CH3, this is a CH3. Is hydrogen bonded to anything fun? Fluorine, oxygen, or nitrogen? Again, directly attached. Is any of my hydrogens? Great job. I like to see that you guys answer no. Look at what it's bonded to. It's bonded to carbon. Okay. Since it's bonded to carbon, understand that this cannot have hydrogen bonding. So all of the forces that are going to have is dipole-dipole and dispersion, but the strongest out of the two is going to be dipole-dipole. Okay, so it's going to have all of these. Let's move on to the next example. Here we have an alcohol. Okay, this alcohol specifically has 5 carbon atoms. Okay. So let's understand that in this molecule that we have 5 carbon atoms. Go back into the knowledge of polarity. I want you guys to, remember. What would you say? Is this polar or non-polar? This molecule, it has OH. What would you guys think? Based on the rules, think about what we did with the ester. I know it has been some time since we have looked at ionic compound, or sorry, at organic compounds, but I agree with you, Kiyomi. This is a polar molecule. Why is it polar? Because we have a carbon bonded to oxygen. Okay. Now, taking this into account, let's put 1 for yes or 2 for no in the chat. Any molecule, would it have dispersion forces? Yes or no? 1 or 2? 1 for yes, 2 for no. Great. So because this molecule has electrons, hey, it has dispersion forces. Now, we already determined that this molecule is polar. So will it have dipole-dipole attractions? Yes or no? Dipole-dipole attractions. There you go, exactly. Yes, so it's going to have dipole-dipole attractions. Now, one more thing. Can this molecule go and have 8 hydrogen bonds? Can it do hydrogen bonds? What do you guys think? Do we have a hydrogen atom bonded to a fun element? Great. This molecule can also have hydrogen bonding events. So even though it has all of these, understand that the strongest out of the 3 that is going to be present here is going to be the H bonds. So when we look at this, let me give you guys the shorthand of this. If you have a molecule that with the flow chart you determine that it has hydrogen bonding. Anything below hydrogen bonding will also be included. If you have, utilizing the flow chart, a molecule that has dipole-dipole attraction, anything below it will also be included. What does that mean? That if my molecule has dipole-dipole attractions, it will also have dispersion forces. If a molecule is nonpolar, the only attractive force that it will have is dispersion forces, okay? Any questions? Let's finish with the last two molecules, okay? So what is the functional group on D? What is the functional group? Let's do a quick review. Great, that's an amide, okay? Now, when we look at the electronegativity values here, we already know that this is 2.5 for carbon, that this is 3.5 for oxygen. Electronegativity. Nitrogen has a value of 3.0. So does this molecule have polar bonds? Again, taking into account, thank you, Vanessa. Yes. How many, you guys? Let's put it in the chat. How many polar bonds does it have? Two out of the ones that I illustrated, but there's actually about 5 because a nitrogen-hydrogen bond is also polar, okay? So again, but from what I gave you guys, let me just include it so you guys see what I'm talking about. Hydrogen has an electronegativity value of 2.1. So technically, nitrogen-hydrogen bond is also polar. So there's a lot of polar bonds here. So what do you guys think? Is this going to be a polar molecule? Yes or no? Great. So this is a polar molecule. So from what we have discussed so far, okay, and then utilizing the following, A, B, C, and D. This is dispersion. This is dipole-dipole. This is H bond. And this is ionic. What are all of the forces that we can find in an amide? Let's put it in the chat. All of the forces based on the structure and the atoms that it has. So let's put the letters. Love to see those ABCs, okay? A, because it has electrons. Dipole-dipole because it's polar. And H bond because we have hydrogen bonded to nitrogen. So here, for this example, we can have dispersion, dipole-dipole, and H bond. Now, out of the three, which one is the strongest? So if instead of listing all of the forces, if I ask you guys, what is the strongest? Great, H bonding, or letter C, okay? Now, understand that for the purposes of this class, even though this is a really cool molecule, we haven't talked about in depth of how do you deal with a molecule that is this large, and especially because this molecule may look like it has some polar bonds going around. Technically, When we look at it, we can see that there's a nitrogen with a hydrogen, so that will indicate that we may have hydrogen bonding, but having a large number of carbon atoms can also result in something that is nonpolar. So I'm not going to do letter E because I'm not going to test you with molecules that are this large, but I do want to go over F. So let me just cross letter E. But let's move to F. So on letter F, what kind of compound is this? We have potassium, which is a metal, and we have bromine, that is a non-metal. What kind of compound is this? Great, this is an ionic compound. So guess, if you have an ionic compound, what is the only attractive force that you can have? So if you have an ionic compound, thank you, just ionic. So when it comes to this, ionic, that's it, because we're dealing with an ionic compound. So for this concept, I want you guys to picture some of the material that we already discussed. Like, do I have an ionic compound? Do I have a covalent compound? If I had to have a covalent compound, is it polar? Okay, let me see if we got this. So if we look at 7.43, okay, let's put on the chat, which of those compounds will have an ionic attractive force? Let's put the letter. Out of A, B, C, D, E, and F. Which letter corresponds to the compound that has an ionic attractive force? Great job, Katie and Kiyomi. When we look at this, hey, this is ionic. Why? Because this is an ionic compound formed by a metal and a polyatomic ion. Okay? Now, there are two compounds on 7.43 that are just going to have dispersion forces because they are nonpolar. And we talked about these in chapter 4. So what are the two compounds that are going to have just dispersion forces? They are going to be nonpolar. Do we need a hint? No problem. Which one of the two of all of the molecules that we have here are hydrocarbons? Remember, hydrocarbons are nonpolar. Which are hydrocarbons? Great, thank you, Dominique. B is one that has dispersion. Where's the other hydrocarbon? Great, and letter D. Now, if we look at letter C, okay, what is the most likely attractive forces that are present in that molecule? Look at C. Think about the functional groups that we just talked about. What is the functional group there? A carbonyl bonded to nitrogen. That's an amide. And we, oops, sorry. And we already deal with an amide on letter D, okay? So as you can see here, if you have an amide and the nitrogen is bonded to one hydrogen, doesn't need to be two. As you can see, we're going to have all of the forces, H bond, dipole-dipole, and dispersion. Remember, ionic is only reserved for ionic compound. So when you have an amide, you're going to say, okay, that molecule is going to have H bond. Why H bond? Because we have, let me highlight it. The H bond comes from the nitrogen bonded to the hydrogen. It's going to be a molecule that contains dipole-dipole attraction. Because we have, and I'm only illustrating one, a polar bond. Remember that carbon-nitrogen is also a polar bond. And then lastly, it's going to have dispersion forces. Because the molecule has electrons, okay? Now, out of these three, remember that the strongest one in this molecule is going to be those H bonds. Any questions? Trying to find attractive forces in a given molecule. And remember, this flow chart can help you find the strongest attractive force by just simply saying, okay, do we have ions? Yes, no. And then you follow through in the questions that it asks you based on your responses, okay? Great. Since there are no questions, let's move on to the next topic, which is just a little reminder that first, remember that matter can be classified in terms of its physical state, as a solid, a liquid, or a gas. Why is this important? Because in section 7.2, we're going to talk about specifically how liquids and solids can have attractive forces, okay, in them. And depending on the attractive forces that they have, understand that we can find them in the different states, okay? So let's understand that attractive forces are going to be stronger between two compounds that are moving slowly, okay? When we apply heat to a substance, understand that those molecules, particles, or ions that are part of your molecule are going to be moving very quickly, and then attractive forces are going to become less important. Now, let's understand that the changes in state for every single one of the states of matter that I just reminded you guys of is derived from temperature. So remember that all of these changes that we see here is due to changes in temperature. So it is important that we review what are going to be those terms that we utilize for the different changes in state. And as you can see here, if we go from a solid to a liquid, that's known as melting. If we go liquid to a solid, that is called freezing. If solid turns into a gas, that's called sublimation. If your gas gets turned into a solid, that is deposition. We can also have changes from liquids to gas. And when that happens, that's called boiling. And if a gas turns into a liquid, that is condensation. So understand that it is important that we rationalize, okay, the different changes in state are going to be occurring due to temperature, but this temperature that is going to change the state specifically is going to make my substances have stronger attractive forces or less attractive forces. And then as we can see here, which we learned some time ago, the interactions between of the particles, as you can see, between solid, liquids, and gases are different. So remind you from the table, because we're dealing with attractive forces, we're going to be focusing right here. So as things move from solid to liquid to a gas, the attractive forces are going to be less. So the attractive forces that we find the strongest is going to be in solids, then the liquid ones are going to be less strong, and then the gases are the ones that are essentially none, so they're going to have the least attractive forces overall between all the different states of matter. Any questions about attractive forces and states of matter? Now, let's move on and let's talk about attractive forces, but specifically in solubility, okay? So we have to revisit the whole concept of polar molecules, okay? And when it comes to attractive forces and specifically solubility. So solubility, which is a concept that we're going to talk about more in detail in chapter 8, I want to at least introduce it to you guys. Solubility basically states that we're going to have an amount of a compound that is going to be able to dissolve in a specific amount of another compound, okay? Now, how do we know that things dissolve? Well, they dissolve because we have a rule of thumb that determines if things are dissolving. And that rule of thumb, as you can see here, it says like dissolves like. So what does that mean? As you can see in the first bullet point, if you have a polar molecule, you're going to be able to dissolve it in a polar solvent. So meaning the two molecules that dissolve into one another need to be polar. Now, if we relate this to attractive forces, okay, these are the three attractive forces that we see specifically when polar molecules dissolve in other polar molecules. The first attractive force that we see is an ion dipole attraction. And you may be wondering, but wait, Dr. Luz, ions are not polar molecules. I understand that. They are ionic compounds, but this is the interesting thing about ions, specifically if they're able to dissolve in a polar solvent or a polar compound. The reason why they do that, you guys, is specifically because an ionic compound that is able to dissolve, okay, in a polar solvent is going to do it because there's going to be a distinction in the charges. So remember that, for example, here these molecules are representing water, where this is the oxygen and water, and this is the hydrogen. We learned some time ago that water as a molecule is a polar molecule, where the oxygen is delta negative, the hydrogen is delta positive. Now, let's take into account that the reason why they can interact is because the full charge in your ion is interacting with the partial negative charge of your polar molecule. Let me put it in words. The full charge of an ion can interact with the partial charge of a polar covalent molecule. Okay, So as you can see here, the cation in, let's say, in sodium chloride, table salt, is going to be interacting via ion dipole attractions with the oxygen and water. Even though it's not illustrated here, we can envision that a similar interaction can happen with the chloride ion. The chloride ion in table salt can be interacting specifically, let me make that a little bit smaller. They can be interacting with the delta plus in the water. Again, via an ion dipole interaction. And this can only happen if one molecule is ionic and is soluble in the other molecule that is polar. And here we just have salt and water, okay? Now, two molecules can also interact with one another via hydrogen bond. Here we have methanol, okay? As you can see, methanol has an OH group. Water also have an oxygen bonded to hydrogen atoms. Look at the structure. Let me just include the atoms. This is a hydrogen, this is an oxygen, this is hydrogen, this is hydrogen, this is oxygen, this is carbon, this is hydrogen, hydrogen, and the other hydrogen is back here. So these two molecules are going to be interacting with one another via hydrogen bonding because both of them have an oxygen atom attached to a hydrogen. So notice that the hydrogen bonding event between these two polar molecules is going to happen via that fun element, okay, that is found in the water, and that hydrogen that is found in the methanol. We can envision also, you guys, that in addition to this hydrogen bonding event that we see here, that we can have also a hydrogen bonding event. Let me do it as dotted line because it's more appropriate. This is not an actual covalent bond. This is an interaction. That's why I'm going to do dotted lines between the oxygen in the methanol and the hydrogen in the water. It's just that it's not illustrated, okay? Lastly, another attractive force that can happen between molecules, it is a dipole-dipole attraction between two polar molecules. Here we have methanol and chloroform. So let's rationalize why this is dipole-dipole and not hydrogen bonding. Both molecules are polar, okay? And even though methanol, CH3OH, has an OH, why is it that chloroform cannot interact with it via hydrogen bonding? What is chloroform lacking? Let's put that in the chat. Why would chloroform? Thank you. I love your answer, Vanessa. Chloroform is lacking the fun. Hydrogen is not, oh, thank you, Katie. I love that you always support everybody. So hydrogen is not bonded to a fun element. Hydrogen is bonded to carbon, okay? If we do the Lewis structure for this, it's just that it's a little bit hard to see in the structure that we have here, but this is the Lewis structure. And for the exam, you guys, next week, I'm not expecting you to draw the Lewis structures. What I want you guys is to focus on the interaction. So Lewis structures will be provided to you. Now, as you can see, and like Vanessa put in the chat, in chloroform, hydrogen is bonded to carbon. So because it's not bonded itself, okay, to a fun element, that's why these two molecules cannot interact via hydrogen bonding, but they can interact through dipole-dipole because both of them are polar, okay? And we can envision that in that polarity, that's why you see the vector written between the two of them. That's what the interaction is. Now, let's talk about at least the last two before I let you guys go. So when we have nonpolar molecules, they can actually come together with other nonpolar molecules, okay? As we just discussed in terms of attractive forces, what is the attractive force that exists in nonpolar molecules? What is the strongest attractive force that happens in nonpolar molecules? Great, dispersion. So the reason why polar molecules dissolve with other nonpolar molecules, so remember, nonpolar matches nonpolar, is because they both have dispersion forces. So the concept of like dissolves like is that if something has charges, it's either going to be coming together with polar molecules, okay, via ion dipole. If something is polar, it's going to want another polar molecule. And in that instance, we're going to have hydrogen bonding or dipole-dipole. Now, I want to give you guys one last example before we move on. When it comes to some molecules, let's actually show, what they have going on. What if your molecule has polar and non-polar parts? So here we have the molecule that is called oleic acid. Oleic acid is the main compound that is found in olive oil. Now, let me ask you guys, does oil and water mix? Yes or no? Let's put it in the chat. Does oil and water mix? We know that is a no. Great. So, but what if I tell you guys, well, oil has a polar section. It's right here. This part of the molecule is polar. So if the molecule and part of it is polar, why wouldn't it mix with a polar solvent? And let me explain why. I want you guys to focus on the rest of the molecule, which is all of this. What is covering more area? The polar or this area that is non-polar because it is a hydrocarbon? Which one is larger? Great, the non-polar. So even though this molecule has polar and non-polar, the non-polar portion is so large that the molecule is going to be considered non-polar overall. So since this molecule is considered non-polar overall, in order for us to combine it with another compound, can we combine it with something polar or something non-polar? So what would this interact better? With a polar molecule or a non-polar molecule? Thank you, Dominique. I agree. Thank you, Katie and Kiyomi, and also Daisy. I agree with you guys. This is going to interact with another non-polar molecule because even though it has a polar side, overall is going to be considered non-polar. Now, this whole idea of hydrophobic and hydrophilic that is in competition, hydrophilic means an area that is in love with water. So the polar side is the one that is hydrophilic. Hydrophobic means that it's afraid of water. So the non-polar side is hydrophobic. Let me just include it here. So this part is going to be hydrophobic. This part is quote unquote hydrophilic. But in this competition, because my hydrophobic side in this competition is larger, is going to take over the property for my compound. So the best way that we can actually combine this molecule with another compound is going to be via a non-polar compound. Any questions on attractive forces and solubility? Great. Since there are no questions, this is all for today. Thank you guys so much for coming.